Okay, now we are going to focus on three-phase theory. So, okay, we will start. So, we have already studied about the single-phase system, right? So, the related equation on the single-phase system. But we are, anyways, in our domestic level, we are receiving single-phase connection. Anyways, it comes from a three-phase supply, right? So, when you see this picture, you can see that the house is supplied with a two wire. That's mean one is live wire and other one is neutral wire, base conductor and neutral conductor, right? As you can see here, I'll point a laser pointer here. There are two wire, but you can see here in this side four wire would available, right? Four wire. So there are three phases and one neutral. So normally for a house we take one live wire connection and we tap a connection from a neutral wire. So in that way only we load a single phase system, right? Then we reduced into single phase system, but anyways it comes from a four wire system. So before that you can see here a transformer, a step down transformer. Here you can see it is three wire system, the transmission line, everything, the three wire system. The neutral is no more there, right? So in this distribution network only we can have the neutral connection, right? So we will see this in detail in following slides. Okay, if you take a single phase voltage source, it contain a single coil in the sense it has been connected, single winding. Actually it contains single winding. So whatever the generated EMF would produce between these two terminals in the sense, I'll take the pointer again here, these two terminals, with respect to these terminals this kind of voltage would generate. Let's take that is Vt is equal to Vm cos omega t. Similarly, if you go for the single phase voltage source, that's means three phase voltage source, that's means three phase generator, right? So it can produce three different winding would be there, right? So in these three windings, so there would be a different voltages, that's means VAT, VBT, VCT. Then these are identified with respective to different color code here. This is A phase voltage with respect to those two terminals. Then this is B phase voltage. B phase means B winding voltage, and C phase winding voltage, right? Similarly, this kind of three different voltages could produce, right? These three different voltages could be sent through three different lines. That is what we are going to talk about in the three-phase voltage system. So in this way, if you consider in that way, you may know, you can say that there are three voltages. So you can model the source in this way. So it could be connected in this way. So this is the neutral point, can be tapped from here, right? The neutral point can be tapped from here. Sometimes that neutral point would not available. So this is VA, VB, VC. So if you are no need of any neutral point, you can connect your the windings in this way also, the voltage generating terminal windings in this way also. So here these are the point A, B, C phases, and here respective A phase voltage is VA. That means that's phase voltage. Respective B phase voltage is VB, and the respective C phase voltage is VC. That source can be modeled in this way. Otherwise, if you are not going to tap a neutral point, so you can go model it in this way. This model we call delta connection, right? Delta connection here. Then this is A phase and B phase. These are actually here you can see the induced windings are placed in this direction, and the voltage generated along with that will be represented in this way, right? So VAB and VBC and VCA, right? So anyways, the A, B, C is three lines are coming out of the source. Right, if you take real source, so you know it has source impedance. So the source impedance, if the windings are connected in the star, that's in Y format, so you can model in this way with the series winding, just like this. So this is winding resistance of the source and winding inductance, leakage inductance of the source. Similarly, winding resistance of the source and winding leakage inductance of the source on B arm, and on the C arm it has winded. Similarly, winding resistance can be given in this way, and the winding leakage reactance could be given in this way, right? So if you take delta connection also, the winding resistance and the leakage inductance would be connected in the series with the source terminals. This is how we represent real delta and Y connected voltage source. Sorry, the real Y and delta connected voltage source. Right. So normally we are going to study about the balanced three-phase voltages. That means balanced three-phase voltage in the sense. So here VAN, VBN, VCN, that means voltage magnitude are same, and these voltages the phases are placed in 120 degrees apart from each other, right? So you can have two different sequences, ABC sequence and the ACB sequence. ABC sequence in the sense it can be represented in this way. So A, N, B, N will be placed in this way, and C, N would be taken in this way. This is what we call the positive sequence. So if A, N here and B, N in this direction, right, that is positive sequence. Therefore here it is C, N here and V, B, N. This is what we call the negative sequence. So this is what it's given: three sinusoidal voltages of the same amplitude frequency but differing by 120 degrees phase difference with one another. There are two possible sequences, that is ABC and the ACB. That means it is given in this way. So we will move to next slide. So we can determine, so if you place your eye in this position, so you can see, because this is a rotating phasor, right? Actually voltage and currents are rotating phasor. So here when you look at this side, so you can see A, then you can see that the voltage phasor B and C if it rotates, right? So that's why it becomes positive sequence. Then ACB becomes negative sequence. Normally we will discuss about the positive sequence, right? And for the unbalanced network we will discuss about the negative sequence, right? So if you take three-phase system, so three-phase voltage source could be delta connection or the star connection, that's mean Y connection. Your load also could be three-phase load, right? Star connection or delta connection, right? Either one of the configuration would be there. These are the in between, there are three-phase lines would be there, right? If it is star connection, there may be a neutral conductor. It's not necessary. Some type it is necessary. So there would be different configurations in this way. So first we will discuss about the general star, that means Y source or load model with the neutral connection, right? So you know the source can be represented just like this, three legs, three arms, and with the voltage source in this way it could be represented, and there could be neutral terminal, right? And then sometime this load could be represented in this way. This is actually a load, all right? Then ZY, actually it's a balanced load, That's why it has the same impedances in each leg, right? So neutral point can be tapped from here, and when you take this one, right, this one, this is actually line impedances, then it is series with the load impedance, right? So we will move to the this one, general that means star source or load model without neutral. Without neutral in the sense there will be two lines, there are no neutral, so only these three legs are here. Here also three legs are here, so it moves in this way. Similarly, we can have source or load in delta configuration. Okay, you know this is in delta configuration, right? We actually discussed source is in delta configuration here, and the load is in delta configuration here, and z delta, all of them are same, balanced load. Alright, it's an assignment, right? So please try to do this assignment and submit it before next week. So try to submit it before next lecture. So next week in the sense next Wednesday, alright? So we will discuss in class later. Right, we will model this one into equation, right? So three-phase line model can be given here. Actually, this with respect to the neutral terminal, the line phase voltage will be VA, and the B phase voltage would be VB, and the C phase voltage would be VC. Here you see, and VA, this is actually line to line voltage, two lines, between two lines, VAB and VBC, VCA. This is line to VCA, right? Line to line voltage. So actually these currents are sent through those wires, and addition of this current would be equal to the neutral conductor line, the neutral conductor current, that is I0 is equal to IA, this current, and this current. Right. Similarly, VA, VB, VC could be 0, may be 0, may not be 0, right? So we don't know about that, right? VAB plus VBC plus VCA also could be 0, or may be 0, may not be 0, right? Okay, so we will see some definitions with later line model. So phase voltage, the voltage between any one phase or neutral, voltage between any one phase and neutral, or we can say phase to neutral voltage in three-phase network. Right, line to line voltage in the sense voltage between any two lines, line to line voltage. Actually, it's known to be line to line voltage. Then IL, that's mean line current in any line A, B, C. Then phase current in any arm of the line, or any arm of the line in the sense that is actually line, or any arm of the line, or any arm of the load. That's mean it could be connected in the delta or star, right? So any arm of the load or source. If it is delta, we denote the phase current by ID. If it is star, we denote the phase current by IY, right? Then next is neutral current. The neutral current in the sense the current in the neutral conductor. If it is 0 for the balanced system, if it is unbalanced system, definitely neutral current would be there. Then neutral voltage in the sense the voltage of the point of neutral, it is 0 for solid ground system. You don't have to care whether it is balanced or it is unbalanced. You don't have to worry about it. So it is actually if it is grounded, it is if the neutral point is grounded, it is 0. The voltage of the point is 0. So here we will see the balanced three-phase system. So in balanced three-phase system, the I0, that's been the neutral current is 0. The I0 actually, if you add those phase currents, you will get I0. That I0 will be 0 for the balanced three-phase system. As well as VA, if you add VA, VB, VC also equal to 0, right? Then VAB, VBC, VCA, that's been line. If you add line voltages, the sequence A, B, B, C, C, A in the sequence, that also gets to 0, right? So we will move on. If then we are bothering about the ABC sequence, the positive sequence, right? So here we can draw the graph VA. So I'll take the pointer here, VA here, right? And the VB here, this is actually VB, and VC here, right? VA, VB, VC, those are phase voltages of each line, right? So let's say the load is with a lagging power factor cos theta, then you can have the angle IA and for angle theta between VA and IA, and VB and IB, and VC and IC, right? So once after that, so we can find the line to line voltage VAB, by subtracting VA minus VB. So if you subtract, means you have to construct a line minus VB here, and you use the parallelogram theorem to add those two phases. So at that time you will end up with VAB. So VAB is equal to, the VA and VB magnitude, both of them are same, but the direction between the angle between the VA and minus VB, that means it would come here, that is equal to 60 degree. So the VAB will be in this direction with the 30 degree phase shift and root 3 magnitude transformation, right? So you will get VAB. Similarly, VCA also is a 30 degree phase shift, you will get VCA. Then similarly you will get VBC with the phase shift of 30 degree from the VB, and it would be transformed by root 3. It would be multiplied, magnified by root 3. Then you can see all the line voltages are multiplied by root 3, and it has a phase shift with the respective phase voltage, right? Then we can say that is EJ30. This is the phase shift, right? We can get an equation in this manner. Similarly, the line current here is equal to the phase current, because we are bothering about line. Normally line current is always equal to phase current in the line model, right? Then this is ABC sequence. So this is how we normally draw. First place VA means this is VA, right? It is here. VB, it is minus 120 degree lagging. Then you will start minus 120 degree, means here you will start with the plus. So here you will start here from here, then you can complete this part in this manner. And VC also you can VC means this one also you can draw in this way, right? VC also draw, you can draw in this way. Now we will see furthermore the balanced three-phase phases. So you can reduce all the phases. That means all the phases are same, right? Same as this one, right? So it has a 120 degree phase shift. Here B phase has minus 120 degree phase shift. C phase has plus 120 degree phase shift. So you can model the equation in this way, right? In this way. So all the phase voltages are here, and with the line voltages 30 degree it has phase shift, and it would magnify by root 3 with respective to this phasor. That means each phase voltage, and with the load power factor the load current forms. Then this is the load current, right? You know that let's say the ZP, the impedance in each phase of the balanced load of Y equivalent configuration, and it is equal to ZL, right? That is equal to ZL. Let's say that is equal to ZL. Then VP phasor is equal to ZP phasor into IP phasor. Each phase, if you are considering each phases, you can write this equation, right? Then if you multiply this one both sides, that means root 3 is about J30, root 3 is about J30 both sides, you will have this equation, and you can substitute for this part that VLL. So you will get VLL is equal to root 3 ZP that complex number into IP phasor e to the power J30. Right, so that you can have the equation, you can rearrange the equation in this way, right? Similarly, S3 phase in the sense this one, the power, so complete complex power, right? That is equal to, there are three phases, that is equal to 3 into VP phasor into IP phasor conjugate. For this IP phasor, you can put for this VP phasor, you can put this equation, and you will end up with this equation, that is equal to S3 phase is equal to root 3 into VLL e to the power minus J30 into IL conjugate, right? So balance 3, we will move on again, right? So if you so these are the two equations we got so far, right? If you consider that line voltage in the another notation, that means if you have VL, if you consider line voltage in direction with VP, that means here we are having a small notation, right? Small notation. That means line to line voltage always is leads phase voltage. That means in positive sequence it leads phase voltage by 30 degree, right? So we if you consider that V line to line voltage, we shift this voltage in this direction, in the sense you are multiplying with this V line to line voltage with e to the power minus J30, you will get that V line voltage, right? This voltage, that is equal to root 3 VP. That means root 3 VP. It is just root 3 times of VP phasor, right? In other notation, right? So in that way we can substitute VLL e to the power minus J30 as VL, and S3 phase is equal to root 3 VL into IL conjugate, IL phasor conjugate. So these two equations are the final equation to move with any three-phase network, right? So from that we will analyze So if the load is star connected load, right, if the load is star connected load, right, this is the model what we have now. You don't know, you don't know what is inside the load, but if let's say it is the star connected load. That means that by each arm it is a balanced star connected load, so that by each arm has that by impedance. If it is so, so we will see what is the line voltages and the phase voltages inside the line voltages and the phase voltage, as well as line current and the phase current, line impedance and the phase impedance inside the load, right? So VL is equal to, you know that, line to line voltages voltage into e to the power minus 30, that is equal to root 3 Vp. That means this is the relationship between the line voltages and the phase voltages, right? So it is in this way. So here you see the same current, the I line current only flows through this conductor, right? This one, that is, all of them are equal, so it gets to 0 also. So if you add all the phase currents here, it gets to 0. Therefore the I line current is equal to each phase, each leg, each arm of the star configuration. So I line current is equal to IY equal to IP, that is the phase current also. Similarly ZL is equal to ZY, that is equal to Z pi. That means line impedance is equal to the one arm impedance of this the star connected load, right? So we will if we analyze, if we consider the load as a star connected load, so we can have these equations, right? So by applying each equation, you can get the equation for each phase. So let's say if we apply this equation here for VLL, root 3 Vp, and for IL is equal to IP, and ZL is equal to ZP, then root 3 cancel off. You will get the single phase equation by using this equation, right? Single phase equation for each arms, right? So we will show that line impedance ZL is equal to ZY, that is the impedance of the star connected load in a single phase, in any phase of that star connected load. Z delta over 3, actually here Z delta is one arm impedance of delta connected load, so that is equal to ZL, because Z delta over 3. So we will prove this equation, right? First place, you know that we can write a equation in the delta connected load at the terminal A. At the terminal A, the current entering through that terminal is IA, that passing through these two impedances, so that is equal to VAB over Z delta. If you consider this arm, AB arm, if you consider AC arm, that is equal to VAC over Z delta. So you can write VAB plus VAC over Z delta. So if you consider the phasor diagram of this one, so that VAN is equal to VAN, VAB and VCN will be in this way. The phase voltage, the line voltages are equivalent to this line voltages, right? So because these are symmetrical, same system, it is modeled in delta connected load, this is modeled in ZY star connected load. So here VAB is here, that is this voltage VAB, that so VAB can be taken here, VAB here, VCA will be here, therefore VAC will be opposite direction to that VAC will be opposite direction to that one, because VCA will be here, right? So VAC would be here, so VAC, then VAB is equal to root 3 times of VAN into e to the power j30. Similarly, VAC also can be, this is also 30 degrees. VAC also can be stated that root 3 times of VAN into e to the power minus j30. So that is what it's written here, right? Then VAB plus VAC is equal to 3 into VAN. You can take VAN outside, then root 3 times of e to the power j30 plus root 3 times of e to the power minus j30 will be equal to 3. You know, if you take a parallelogram, if you draw a line root 3 in the 30 degree angle and minus 30 degree angle another root 3, if you add up both of them, root 3 times of a particular side of the parallelogram, that is root 3, right? That root 3 into root 3 is equal to 3. Then VAB plus VAC equal to 3 into VAN. So if you substitute for this one, you will get this equation 3 VAN over Z delta. Then the VAN is equal to V Z delta over 3 IA. Therefore, that ZY is normally, if you consider this one now, we can write VAN equal to ZY into IA, right? VAN is equal to ZY into IA. There is no more current, right? Right. VAN equal to ZY into IA. So we can find that, then this is equal, Z delta over 3 is equal to ZY, right? ZY. Actually, earlier we found that ZY is the ZL, right? So ZL is equal to ZY equal to Z delta over 3. Equivalent line impedance of a delta connected load will be divided by 3 of one phase, any phase of the delta connected load, or any arm of the delta connected load, the delta over 3. So we will move with this knowledge. We will move. Let other slide, that is, let load be in balanced delta configuration. So in that case, you know that this VAB, VBC, VCA will be in this way. That those VAB, VBC and VCA are the phase voltage, line to line voltages. So it appears across each phase or each arm of the delta connected load. So you can consider a phase voltage by considering artificial neutral, or if you by considering a particular any other neutral, you can take the phase voltage of the phase voltage of each line. So that is equal to VA. Then line current IA, IB, IC are depicted over there. Then you can take the phase current or the arm current of each arms of the delta connected load. That is, here that is IAB, here that is IBC, and this is ICA, right? This can be found. So from that we will draw the phasor diagram. So you know that, so we can find the, this current IAB, because initially if the load is cos theta lagging power factor, each arm current, each phase current, we will say each phase current of the delta connected load will be theta lagging theta angle phase shift from the VAB, the line to line voltages, that is here. So if you take each phases, you can see theta lagging, theta angle lagging with respect to the line to line voltage. right? After that, we are interested on line current. The line current is equal to you know that this line current is goes through here and here. Here IA is equal to IAB minus ICA, right? My IAB minus ICA. So we will calculate IAB plus IAC. Then we have to we know the ICA. We have to construct IAC. So we construct a parallelogram in this way, and we find the IAB. You know that. So this IAB and the IAC are equal and apart 60 degree between them, right? The angle between them is 60 degree. So the IA is equal to root 3 times of IAB into e to the power minus j30. So if we draw these things here, so these things here, you will get a line. This is repetitive for each and each phases, right? So this is A phase, and this is for B phase, and this is where C phase. Though, so we will consider a line or particular set of voltage and the current. So we take this one, the A phase, and we draw this as a line to line voltage, and from this one, from this phase or this arm, other phase voltages and the voltages and current are 120 degree apart from each other, right? 120 degree shifted, right? Then line to line voltage, that is actually VAB, so we mark in this way. ID, that is actually the phase current of the arm in the delta connected load, that is ID, it's here. And you know that the line current, that is IL, that is equal to root 3 times of the delta connected load arm current, the phase current, into e to the power minus j30, right? So similarly, VA is equal to, you know that if you don't consider, if you are having a black box on top of the delta connected load, the V, you know that you don't have to worry about this part, that VA, that phase voltage, will be equal to you have to divide the line to line voltage VAB by root 3 and e to the power plus j30. So that is equal to, then you have to phase shift by minus 30 degree, and you have to divide it by root 3. Then it comes here, right? So you know that early equation you found the VP into VP times of root 3 VP will be equal to VL. So this is what we are having. So if you are getting in line with this equation, so we should consider this VL by not to consider this one. So we have to consider this one. So this part of the voltage, this part of the line current voltage, and this part of the line current, this phase diagram of the line current and the phase diagram of the line voltage, right? So you have to consider in line with the phase angle, in line with the phase voltage, right? So if you take this one, you can apply this equation. So for that, so you know that VL is equal to VLL into e to the power minus j30. It says there. Then you know that is equal to root 3 into VP. Then here IL is equal to you know that root 3 into ID e to the power minus j30. Actually this is the phase current in the line, right? That phase current in the load is equal to ID, right? Phase current in the load is ID. Phase current in the line is IP, right? That is actually here we are considering this part, IL, right? Then IL is equal, ZL is equal to Z delta over 3. You know, equivalent impedance of that one will be Z delta over 3. We proved just before, that is equal to ZP. Right. Now we will move to three-phase equivalent per phase model. Three-phase equivalent per phase model. You know, this is three-phase system, right? So it can be represented by a single phase system. That is actually not a single phase, it is a three-phase equivalent per phase model, right? So this system can be represented in this way. Then this is the line IL current, and plus or minus VL, plus here and minus here, this is VL, and here ZL is the load, reflect line load, right? Equivalent line impedance, right? So here three-phase power, the active power is flowing in this direction to the load, and the reactive, we take the reactive power also flowing in this direction to the load. Then VL is, you know, with this equation we can represent this complete three-phase load into a single phase model with this equation. You know that you by Ohm's law, you know that V equal to IZ, right? But here it seems like it's violating, right? So no, because it is this is not a single phase system, this is three-phase equivalent per phase system, right? So it is it seems like violating, but it is not violating. Here also you have studied in a single phase system, S phasor is equal, that complex number, the complex power is equal to VL into IL, right? But here root 3 terms comes here, VL into IL conjugate, right? Root 3 times comes here, so because it is not a single phase system, this is actually three-phase equivalent to per phase system. So that's why this kind of root 3 comes here, right? So you may represent, by using this equation, inside this equation you may have different set of equations. So you can you just try to do it with yourself, so you can reduce into these equations, right? So let's say that ZL is equal to R jx, ZL is equal to ZL theta, that is equal to R plus jx, right? So we can draw in this way. So since it is a lagging, it's an inductive load, you will have a lagging current with the line voltage. So it will be in this way. Then IL have two portions, IL cos theta and this IL sin theta. The IL sin theta is equal to J, actually it's a imaginary component. So J IL sin, that is actually minus J IL sin theta. Then you can substitute this IL phasor as IL cos theta minus J IL sin theta conjugate. So S3 phase is equal to this one, the root 3 VL IL cos theta plus J into root 3 VL IL sin theta. So this portion root 3 VL IL cos theta is equal to three-phase power of the system, right? Early days you got the single phase power VI cos theta, right? Single phase active power. But here root 3 terms comes here because it is a three-phase equivalent per phase system. As far as Q3 phase is equal to root 3 VL IL sin theta, right? So we will move on, right? We are trying to do an example. 400 volt line to line voltage and three phase 7.5 kVA load with 0.8 lagging power factor, right? So there's a load actually with the line to line voltage is 400 volt and the 7.5 kVA is a 7.5 kVA load with the lagging power factor 0.8. So you should find out the line current. So S3 phase is equal to 7500 cos inverse 0.8. it is, since it's lagging, so here you know the current is negative, it goes to the negative angle, but the power comes to comes to a positive angle. Then 7500 cos inverse plus cos inverse 0.8, right? So using this equation you can find IL. You know, let's take the VL is equal to 400 because line to line voltage is as a line to line voltage is 400. By taking it as a reference, so you know that we can find the current on the line, that is equal to 10.825. It is 36.87 degrees amperes, right? So similarly we have to work other three example: example 2, example 3, example 4. So we will try this one on the board, right? Thank you.